Hi, I'm Sanjana. I'm a junior in mechanical engineering, and I'm really interested in robotics, SFX, and mechatronics. So I thought it would be cool to use this project to put speaker verification on a microcontroller to be used in robotics. Here's my mechanical design. It consists of a resin printed face finished with chrome paint. Hopefully that looks really cool. The user experience basically will be you go up to the robot has some idea of who it wants you to be, who it wants to verify you as. And if you are verified, then the robot's eyes will glow, smoke will come out of its nostrils, hopefully. And if anybody has any interesting effects that could be a cool response, please email me. I love these cool ideas. And then the circuit that is inside the robot consists of a microphone acting as a biometric. The microphone will amplify the audio signal, send it to the analog to digital converter in the microcontroller, which is the ESP32 by Espressif. And then the microcontroller will segment and sample the audio for processing and to get various parameters that we can use for verification. For the data sets, I'll be using Tedlium just for training and enrollment. I also will have to enroll myself in the data set so that my own robot can verify me. Caldi might be a little bit too intense for a microcontroller. There's not much literature with people using Caldi on an Arduino, ESP, or Raspberry Pi, but there's a good amount of literature where people are using CMU Sphinx or Pocket Sphinx, so I might use that for this specific use case. I think it might be a little bit more appropriate. For recognition and the testing phase, I won't go through all of this because it would take more than a few minutes. But basically, the waveform we would put through a fast Fourier transform just so that we don't have to do a full Fourier transform, takes a little bit less time. And then we have something that we can operate on. We would put that through a filter bank to reduce the number of coefficients we work with. We'd also there get a vector associated with energy. We'd get something called filter bank energy, or FBE. From there, we apply logarithmic compression to the FBE to obtain some coefficients, the Mel frequency substrate coefficients. And then we now have 4 parameters that we can use to verify the speaker. We have fundamental frequency, we have jitter, which is a periodic deviation, we have shimmer, which is a difference in amplitudes, we have the Mel frequency substrate coefficients, and the UBM. And the UBM is a function of the Mel frequency substrate coefficients and the previous FPE that we found. We put it through this equation at the end, and we are verified. The number one thing that I expect as a result from the literature and from mathematical thinking that I did is that the time it should take for the robot to verify the speaker is approximately 4 times the length of the audio signal. That could be decent if the audio is something like "Hi robot, it's me," but that could also be really long if the audio signal is longer. So that's one obstacle I'll be working with. This is the beginning of my project. It might be altered, but yeah, I hope you really enjoy it. Thank you.